we might be able to build, or what we're hoping to build, potentially beyond the store program architecture and Moore's law limits. So just to give a general overview, if we don't talk about anything else, this is the whole presentation in one slide. So really what's coming from neuroscience, basically the inspiration from the retinal implant, cortical implants, lots of other things, the connectome, retinal connectome, human connectome. There's an incredible amount of data that's coming in that's getting better and better and actually becoming a lot more detailed and much better understanding. Thing about what's currently being done, there are actually things out there that are operating right now. Actually, there's some in the back of the room right now. People have been looking at probabilistic Bayesian computation and trying to leverage some novel architectures to do things sort of beyond the bottlenecks that we've been talking about. And what we're really hoping to do is then take all of these and kind of take them into the future where we can come up with this new computational approach. And there really is a convergence that's coming from neuroscience, from microelectronics systems and devices, and into computational systems. And again, as we talked about briefly before, from the technology side at least, there are two limitations: the end of device scaling from Moore's law, and the power limitations in terms of systems, and actually from the application side, being able to deal with the large incomplete sort of noisy natural data sets, kind of the big data kind of problems. This overview I presented earlier, again, our problem is that we can't address these highest impact problems the best we can. The challenge is how do we figure out what's coming next? And the potential impact is, again, in some of the for the first users in national security applications, looking at the industry, saying this is just microelectronics by itself is $300 billion a year, and then there are trillions riding above on top of that in terms of the computers, the IT, basically all the other economy that's been enabled by that. And then the game theory, how do we actually find out, how do we study how people interact, how they make decisions, how do societies in the end interact. So maybe jumping to the end of the talk, this is what we're hoping to build. Again, there were some really interesting, great talks. What we propose here is just one example. There might be lots of other instantiations of what this might be, but what we're hoping to build is a device that has some nominal unit cell, that has local interconnects that are mostly optical and electrical, some medium range interconnects that are, again, optical and electrical, and long range inputs and outputs that are most likely going to be optical. Again, this is somewhat leveraging the thoughts and some of the concepts out there already in terms of the cortical columns and kind of the massive interconnectivity that's in the cortex. And one of the, I guess, couple things to point out here, the key characteristics of the cortex, of the neural structure. First one is the plasticity and adaptability of that substrate at the lowest level device possible. So it's basically the smallest unit that you can get to, that you can modify. You'd like to have access to that. And the other key characteristic is the massive interconnectivity, sort of single neuron having 1,000 to 10,000 synapses onto it, and then kind of multiplied from there on for the whole architecture. Again, we might not be able to replicate that completely, and maybe we don't need to replicate it in all fidelity, but achieving something that's close to that is really what we're after. So looking at neural computation as an inspiration for the computational architecture, again, I've shown this slide earlier, but neural computation is not a von Neumann architecture system. It does pattern recognition, abstraction, prediction, and adjustment, which is basically learning. It's dynamic and multidimensional. Again, it's a difference engine and accumulator with goals, and those goals are very biologically defined as acquiring sustenance, avoiding predators, and reproducing. One of the key questions here is how is data represented, stored, processed, recalled? Again, this is still an open question. We're getting bits and pieces of the answer from lots of different places, but we still have to merge them to make them useful somehow. And this is the point that I mentioned a little bit earlier. The biological substrate we have is an existence proof, and by no means it's the optimum solution. We might be able to build things that are potentially way beyond in terms of performance, in terms of what they do and how they then integrate back into our conventional computational systems or into biology. Now looking at the Neocortex, or actually the biological substrate, and the CPU, GPU, they're actually not a whole lot different until you, okay. Physically, dimensions, 10 billion neurons, about 4 billion transistors in a modern CPU. You might wave your hands and make an argument that they're not all that different. But once you get to here, they're completely different. The way the cortex is interconnected and the synapses compared to what the standard computers do in terms of 2 to 4 interconnects from one transistor to the next set. And the way they do computation, again, is completely different, and they excel at different things. If you look at the biological substrate, it's dynamic, fault tolerant, and low power, let's say 20, 25 watts for the whole thing. And if you look at how many clock cycles it takes, let's say from photons in to perception of an object, let's say cortical column, 10 milliseconds per layer, and about 100 milliseconds for conscious recognition of an object. In 10 steps, you've gotten from photons into some very high level functionality, and it will be incredibly hard to do that in any other system right now. And again, you can go back and look at the CPU or GPU. It does incredible things very fast and very precise. Actually, it has to be exactly precise for it to be what it is right now. But again, they are designed for, and they do completely different things. My earlier point, to reiterate again, the most powerful system is probably going to be at the merger, is going to be coming out of the merger of the two, where you need exact things. Part of the system does that, and the other system that's doing kind of the object recognition and abstraction is another type of substrate that's hooked up to it, either as a coprocessor or as a scheduler that's running above it. So now what we're going to build conceptually might look something like this. Inside, again, there's what we've been terming a unit block that has certain functionality. I'll get into that in a little bit more detail. Now, how we're going to build it is kind of the question we have for the community at large. We have some unique devices. I'll talk about some of them here. There are other devices in the community that we're hoping to leverage. But how do we then interconnect them? What do they do? What's the primitive in terms of computational functionality? What do they do? Those are going to be the kind of the challenging problems that are facing us in this field. Maybe talking a little bit about what's currently out there. This is one of the companies that I've been, some of the colleagues that I've been talking to, Lyric Semiconductor. Unfortunately, the details aren't showing up here, but they're doing probabilistic Bayesian computation in CMOS, which is really interesting, really exciting. And as an example, what they're able to do is, let's say, parity check functionality in data that's coming off of flash. In standard digital design, they're taking about this much real estate. The same function using probabilistic approaches they're using is implemented in about 1/10 the space, maybe 1/30th the space on a silicon chip with about 1/10 the power. Again, not building this up any higher in terms of hierarchy and architecture, just that is very appealing in many different applications. Another example, again, colleagues from Cognimem are here, and they have some demo systems in the back of the room. Being able to do certain functions deeply in hardware with incredible energy savings and incredible timing precision. For example, being able to compare thousands, tens of thousands of objects to one input pattern within 10 microseconds with fairly low power dissipated. There's some really neat things that could potentially come out from that. And what we're hoping to do is then learn from those examples and hopefully merge them to kind of bring about what might be coming in the next iteration. Again, that's kind of the future architecture we're talking about. So again, what we're hoping to be able to enable in a substrate like this is the massive interconnectivity and the reconfigurability that's inherent in the neural substrate. Now, I'll talk a little bit more in detail now about some of the devices that we're investigating for this kind of an approach. We've built some silicon nanowires that have been embedded in CMOS. Again, this is by no means unique, but there are some interesting things in terms of electrically how they behave, and we might be able to leverage that to enable some of the functionality that we're after. But I think the more interesting possibility is a device that's sort of schematically represented here. And I'm sorry for the projection here, but you can actually, this is a cross-section TM, you can actually see individual single atoms inside this picture here. You'll just have to take my word for it, but what we're hoping to do is then take that device and layer 3-5 semiconductors on top and allow it to emit light embedded in CMOS. And this is a functionality that the semiconductor industry has been after for at least 2 or 3 decades. Things have been tried in several different approaches. They work in small scale, but they have been really hard to make reproducible, reliable. But we think we have a potentially pretty good shot at that because of the unique physical structure that's afforded to us by the silicon nanowire that's going to allow the 3-5 layers that are going to be deposited epitaxially grown around this to relax and stay in high quality. Where in some of the other planar approaches, when you start doing that epitaxy, the lattice mismatch you have between silicon and the 3-5 layers is so great that you immediately start generating lots of defects, and the materials you end up with are not all that functional or all that great. Again, the key characteristics a device like this is going to potentially give us is the plasticity and adaptability at the very lowest level possible, and the massive interconnect and fan out at the system level. Now, you might ask, well, what does this do in terms of the interconnectivity? If you think of this as a communications network, this becomes the optical interconnect backbone for the rest of the architecture, where you can do wavelength division multiplexing or code division multiplexing, time division multiplexing, whatever you choose to do. So here's a notional example of how you might integrate a device like that. Let's say this is that kind of a schematic representation of the device that I was showing earlier, where it has an electrical channel, an optical channel, and an optical channel is this white line here. We might put another device, for example, a optically modifiable memristor that has certain properties based on the light and the electrical impulse that's presented or kind of impressed on top of it, and then a conventional floating gate transistor. And then we interconnect them in some arbitrary fashion, and there are optical and electrical sort of buses that are available, and then that forms a building block for the rest of the unit cell, the rest of the architecture. Now, thinking in a little bit more detail about what the unit block does, it's basically a 6-port cross-connect that lets you take in optical signals and electrical signals, impress optical and electrical control signals on top of it, and then present output signals both in the optical and electrical channels with some internal optical memory and electrical memory. Again, this is completely arbitrary at this point. There is really no functionality that's implied inside the unit block, but again, depending on how the architecture is put together, then this unit block then lets you build kind of the rest of the architecture. And again, at a very notional level, if you look at how you might put something together that has many unit blocks together with optical channels and electrical channels sort of embedded inside a unit cell, what might look like a cortical column, and then how it then gets connected to long-range interconnects and then local interconnects. And this starts somewhat looking like the cortex, where this is the gray matter, and the optical channels, long-distance optical channels, are actually the white matter that's carrying long-range signals. So I used this slide once before, so excuse me for the repetition, but if we do build something like this, most likely we're going to end up using it for entertainment. So actually this is from Feynman's second nanotechnology talk. The first one was Plenty of Room at the Bottom, where he kind of launched the nanotechnology field. And this is maybe 20, 25 years later. He's actually had time to see sort of how microelectronics, nanotechnology has kind of come together, and he has actually some really interesting comments, talks about quantum computation, adiabatic computing, and things like that. And he comes to a point where he says, well, I figured out what this nanotechnology thing is good for. We're going to build this nanobot, it's going to battle a paramecium, and we're going to sell tickets to it. So that actually might have been the, the fun generator that we need right now. So some of the potential applications, Again, being able to do native probabilistic computation, again, that's deployed in many different areas, robotics, communication systems, onboard decision support, where you actually don't have to download the gigabit data stream down to a server rack to do your image processing, but you send back just a few bits of information to say, well, there's a chair, there's a table, the door is over there, and a lot of the communication problems are avoided by that. Potentially unhackable, non-reverse engineerable systems. The example I usually give for that is the cortex, actually the retina and the visual cortex. We have incredible amounts of data, incredible amount of knowledge about the retina, how it functions, and what the visual cortex is doing. We still don't know how the information is encoded. Again, I might get some tomatoes on that one, but now imagine a system where it's trained in a similar way that you're able to arbitrarily demarcate and separate. How do you figure out how information is being passed back and forth? Again, looking at large data sets and data streams where you do anomaly detection and fraud prevention without needing megawatts of power, steady power supply. And modeling of large complex probabilistic systems where we're looking at how, in the end, actually humans behave, how societies interact, and how we value things at the end, what really drives us. And that one point I made earlier in terms of uncovering patterns not readily observable. Again, there's this deluge of data that's coming at us, and there are tidbits of information that's embedded in that. How do we get the value out of that? And going back to neural prosthesis and augmentation, if we can figure out how neural encoding is happening in the first place, then there's actually very fertile ground to then take this back into the biological space again to provide the link between electronic and biological systems. So what we're hoping to do, and we're really excited about this workshop as being potentially one of the nucleation points for this activity. We have certain capabilities at Sandia that are in simulation and modeling of systems and extraction of algorithms and novel devices and fabrication capabilities. And we have active collaborations with the neuroscience community that we hope to leverage, that we hope to bring up to a higher level of interaction. We also have industrial collaborations with microelectronics and other technology companies and customers, potential customers that we're interacting with. And again, this is hopefully the first in a series of workshops, either here or other institutions that we'll be able to hold together, that bring together all the people that are interested in this area, and then proceed forward in terms of enabling the next steps as teams, as new initiatives that come out in this field. So I'd like to thank you for your time, and then if there are any questions, I can answer them, and a little bit after that, we'll hopefully bring all the speakers up to the podium and then have an open mic, open discussion session. So, any questions?
The system you propose looks very interesting, and I'm sure you can do all these wonderful things which you propose, but what I'm asking myself, is it really necessary that right from the beginning you make your life very hard by introducing all these new technologies? I mean, wouldn't it be wiser to just build a system that is based on state-of-the-art CMOS, maybe some other fancy thing, but where you don't have to worry about integrating all these technologies, but really concentrating on the architecture and demonstrate that this kind of computing really works?
That's actually a really good comment. I didn't highlight that in enough detail in my talk, but what we're hoping to do is doing the simulation and modeling of this new architecture in conventional systems, potentially seeing how we might be able to implement it in either CMOS or maybe slightly tweaked CMOS, so we don't have to then push all these new novel devices in from the get-go. But those are all sort of simultaneously proceeding efforts, so we can use both the simulation, kind of the conventional systems architectures, and then these new devices to kind of march forward and also sort of cross-pollinate each other, because there might be certain cases where on the simulation side, one of the big questions is how much fidelity do you need to actually get the functionality you want? We might figure out that as we're implementing some of these hardware test platforms that we find out we can implement this kind of functionality without needing all this extra deep level, let's say, ion channel dynamics. So again, in that sense, it's not just all the devices push forward, but it's neuroscience, algorithms, devices, and architectures, and actually applications. I didn't point that out, but we have colleagues that are going to be presenting some of our potential applications and seeing, and sort of highlighting what is needed in potentially systems like these to solve some of the problems, and using those applications as sort of the kind of the acid test to say, well, are we providing something that's of value in this application space, and then use that to sort of feed back and forward. And your point is very well taken in terms of how hard it is to try to push some novel technology into mainstream computing applications. Basically, it's impossible unless there is a very big driver, a very big pull for it from some other direction. So if there are no other questions, let's go ahead and ask the speakers to come back onto the podium, and then we're going to ask all the speakers to maybe highlight one or two things they've seen during the day that jumped out at them, and if there's sort of in their thoughts or what might be sort of the kind of next steps that we could take concretely maybe at the end of this workshop or some of the collaborations that we might want to pursue. So